So this is a sea star, and we'll be doing a sea star dissection. This is a complete specimen, and this is the aboral surface, because the other side is where you have the mouth, and obviously the side where you have the mouth is called the oral surface. So this is the bottom side of the animal, which is where you find the mouth. The mouth is located directly in the center of the animal. These sea stars actually belong to a group called echinoderms, and echinoderms are characterized by many things, but one of their most obvious qualities is that they have what's called pentaradial symmetry. And so they have radial symmetry, meaning that you can pretty much split this animal. You can't say left and right because radially symmetrical animals don't have a left and right, but radially symmetrical animals can be cut pretty much in half if you were to take a line down the midline that goes through the center. Like, so for instance, if you were to take you were to be able to stretch this guy out, and you were to take a line and just cut directly from here down through here, you could see that there would be pretty much equal halves. And so that's sort of a signature of a radially symmetrical organism. And these are echinoderms, and so they have what are called pentaradial symmetry, meaning they're radially symmetrical, but they always have major structures organized in sets of 5. So in the case of the sea star, they have arms in sets of 5. So this guy has 5 arms. Okay. So again, this is the oral surface, and this is the aboral surface. Some of the things to note on the externals. First is, if you'll notice, there is this little dot right here. In the living specimen, this tends to be bright orange, and that structure is called the madrepori. Probably wondering what that's for. You can imagine that this structure is something like, you can think of it sort of as the kind of like a sink covering, in part because the animal itself is organized. You can think of the internals of the animal as pretty much a pretty fancy, sophisticated set of tubes within tubes, and overall sort of a giant plumbing system. And this is the major in and out for which water can go in. A little bit more about the overall structure of this animal. This animal does not have a vertebral column, but it is able to form its body into sort of a rigid stance, and the way they do this is by drawing in water. They have what's called a hydrostatic skeleton. What that means is that they have a skeleton made of water. Now this little dot right here, the madrepori, regulates how much water can come in and out. The more water that comes into the madrepori, the more rigid or more stiff this animal can get, which is important because these guys live in the intertidal zone, and so if there's a lot of waves and stuff crashing, you might want to be stuck to a rock really tightly to avoid getting pried off by crashing waves, and that's when stiffness matters. If this animal wants to become more mobile, what will happen is water would leave out this same hole, making the animal a little bit more limp so that it can crawl around and hunt and be more maneuverable. And so this little hole is really important. I mean, this little cap right here is really important because it's kind of like it's sort of major access to the internal plumbing system that we will see in a moment. That's the major quality that probably the biggest obvious structure that occurs on the outside on the aboral surface. We'll flip over the animal. This is the oral surface. Again, this is the mouth in the center here. What's unique about this animal is that its stomach, which is located just beyond the mouth, its stomach can actually leave the organism, and these guys are very specialized to eat many kinds of animals, but in particular bivalves like clams. And typically what these animals can do is they will literally crawl up to the open face of a clam, just wrap around it, use their suction cup arms to pry it open a little bit, and the stomach, which would come out of here, would literally fall out, it would more like crawl out of the animal and the stomach can actually digest things outside of its body before the nutrients can be absorbed back in. And so in the case when it's eating a clam, this animal will literally crawl up, wrap around the clam, make sure that its mouth is near the gape of the clam. Once these sucker arms the suction cups under the arms of this animal can pry the clam open just a little bit, the stomach will actually leave. It's still attached to them, but it will actually sort of crawl out, go into the body of the clam, digest it. Digestion occurs outside the body in the case when it's digesting a clam, and then once everything is done, the stomach gets absorbed back in with the nutrients that have been sort of produced from the digestive process. I hinted at structures called suction cup feet. Now, if you're at all familiar with this animal, you know that that's one of the major qualities on the oral surface. So in the center of the arms, you'll see sort of these thicker lines, and within them, I don't know if you can see with the camera, but there are many little tubular-like circular structures, and these are its sucker tube feet. Okay. So all of these sucker tube feet are actually controlled by the water that comes in through the madreporite, and it'll be more clear when I show you the internals of the animal. That's pretty much the essentials of the externals. You have stomach beyond the mouth, and the tube feet, which have suckers on the tips. And so that's the major structures on the oral surface. On the back side, you have the aboral surface. In addition to all this armor out here, you have the madreporite, which is sort of the main access point for water to get in and have access to the water vascular system that comprises its hydrostatic skeleton, which we'll go into now. Okay. So this is a intact specimen. Now what I'm about to show you next is a specimen that's been dissected. Okay, so the student that dissected this specimen, okay, this specimen pretty much had its top half removed. So you can see, if you were to just compare, this is an intact specimen. The student meticulously and very intricately removed the top half of each of the arms. And so what's since been exposed now is this. And so this is the aboral surface. The oral surface looks just like the oral surface of an intact specimen, stomach in the center. Okay, but the aboral surface is different because it's had its top half removed. The madreporite, can't really see it because it's been removed intentionally. But the thing I do want to highlight here is that we can start talking about the water vascular system that is sort of unique to the echinoderms. What is the water vascular system? Basically, it's its hydrostatic skeleton. It's the set of plumbing that occurs and is connecting all the different parts of this animal that can make it move, make it rigid, make it do what it does to basically earn a living. Just to review, the water vascular system consists of a central ring canal which is connected directly to the madreporite. Now that ring canal is connected also to a central sort of pipe that extends down the midline of each arm in this animal, and each sort of central pipe has sort of mini pipes that come out and that reach out to the tube feet. Now, you can't really see it in this specimen, but imagine if we were to zoom in, let's say just on one tube feet, maybe this one. What you would basically see is something that kind of looks like this. Okay, and so this is a squeeze bulb it's a rubber bulb for a pipette, but this thing really illustrates the overall structure of one of these tube feet. So, like I said, if we were to zoom in on one individual tube feet from this angle, so if you were to come top down and look directly from this angle, what you would see are little circular things, and kind of imagine this as being one tube foot that's sort of magnified. If you were to follow the tube feet and go through the sort of the external structure of the animal, okay, which would be located roughly right around here, sort of the central part of the squeeze bulb. On the flip side, you would have the suckers. Okay, now the suckers wouldn't have a hole in here. Imagine this being sort of a flat surface, but each tube feet is associated with the bulb on the other end. Okay, and each bulb is connected to a sort of a mini pipe that connects to the central main plumbing, or main pipe. Okay, and each main pipe is connected to the ring canal, and then the ring canal is connected to the madrepore. What I've just described, the tube feet, the plumbing down the arm, the ring canal, and the madrepore comprises the water vascular system of the animal, the main structural support and locomotory sort of setup, organization in the sea star. Okay, so this is sort of a summary of the tube feet, and whenever you see these guys walking around, when they're walking around their tube feet, all really what's happening is that there's water being controlled coming through this sort of central plumbing system, and if more water gets extended into one of these tube feet, that tube foot will pretty much either extend or retract or become rigid, and so that's how this animal walks on its hundreds of little tube feet on the back, on the oral side. Okay, so that pretty much summarizes the sea star. Again, this is a whole specimen. This is a specimen that's been dissected. Its aboral surface has been removed. And here are the tube feet. Okay. The one structure that I didn't really get a chance to talk about is the stomach, which you can actually see here. This is all stomach. Okay, and usually doesn't preserve well, but this is a thing that would leave the animal when it's about to digest something like a clam. Okay, hopefully this video was informative. Thanks for watching.